Seryoja, so you stop recording, right?
Yes, and I've started a new one.
Ah, okay, so king is dead, long live the king. Okay. Danila, now it's your turn.
Shall I share a screen?
I hope so, right? Okay, so we are going to immediately to the next talk by Danilo Lewanski, and Danilo is now in, I think, in Saclay and IHES, if I'm right.
Yeah, mostly Saclay now.
Okay, so Danilo will speak about a new spin for Hurwitz numbers and Chiodo classes.
Okay, thanks a lot, Leonia. Thanks for the invitation. It's great to be here, even if we cannot be in person. And I think like this conference, the people who had the luck to participate remembers it as a great conference for science, but also for it makes us happy to be humans in a way. So thanks, Elba, also for your talk. I wanted to ask you whether you could say something about the Wittgen's class itself without integration. But it's a delayed question.
Also, Danilo, if you have your slides, can you send it to me? Then I will distribute.
Did you receive them?
Where? I don't know where did you send it.
I sent it to one of them.
Mail or to chat?
Should I upload them in the chat?
Oh, no, it's fine. It's fine. I got it. Go on then.
Okay. So I will speak about Chiodo classes and their applications with a focus on work that we just finished with Alessandro Giacchetto and Ranier Kramer. So thanks, Elba, also because you introduced many definitions that I will use in this talk. So I think this talk makes much more sense now if people are not familiar with those definitions. So I would like to speak about one particular cohomological field theory. This CoFT is the Chiodo class. That is the one in the center. I will call it omega, and it depends again on the genus and on a number of mark points n. And then it has several parameters R, S, A1, AN, and I will define it in a second. And actually in genus 0, it coincides with Wittgen's class Elba was talking about. So you have already an idea of how it is defined in genus 0. And the first point that I would like to make is that Chiodo classes are everywhere in the sense that now we know more and more applications of this CoFT. And it's kind of beautiful how it pops out, and also in very recent works by many people. So the first, just to make it a little bit more concrete, I would like to say that if you specialize all these parameters in the brackets, R, S, A1, AN to 1, what you get is an object that is much more familiar. And also this X upstairs, which is just keeping track of the cohomological degree. So if you take a degree D from the cohomology, you just need to multiply by X to the D. So it's very simple what this X does. If you specialize also X to 1 and all the other parameters to 1, what you get is the total Chern class of the dual of the Hodge bundle. So you will get something that is integrated in the usual ELSV formula. Instead, if you put S equal to R in the formula, you will get specialization of Johnson-Panary-Pandit-Sang ELSV. And then if S is equal to 1, you'll get a relation with the conjecture by Zvonkin that is now a theorem and its generalization. This Chiodo class is also involved in several ELSV formula for Hurwitz numbers of type weighted. So John Harnett spoke a lot about them. They are also in double Hurwitz numbers and in the conjectural formula by Golden, Jackson, and McKeel. They are related to Norbury class, theta. So yesterday I could not attend the talk of Paul because I was flying, but I think, well, I assume he defined theta. And in fact, I will briefly mention how this is related to Chiodo. They are also related to double ramification cycles, which is an object that is quite interesting to algebraic geometers of moduli space of curves. In fact, there is a particular limit that you can take of Chiodo class to recover double ramification cycle. there is a nice relation with Mazovic volumes, and Alessandro will speak about, Alessandro Giacchetto will speak about them in his talk. You can recover the Euler characteristic of MGN open, integrating them in genus 0 that coincide with Witten's class, but in fact for arbitrary genus, there is also a link, and I think this is a work in progress by Felix Janda together with many other people. And then the point of today is that there is a new application to Hurwitz numbers, which I will call spin Hurwitz numbers. And spin, as you know, it's very confusing because there are many spin things in this picture, but what I will specify what I mean by spin. And in particular, I think of them as related to the BKP hierarchy, or in the language of Harnett, the small BKP hierarchy. And then there are more applications. In particular, one is a work in progress with Xavier Blot that I hope I will be able to report about fairly soon. We have a conjecture, and this conjecture says that there is a particular parameterization of Chiodo class that is instrumental to many other classes. It's sort of a universal role of Chiodo class with respect to other QFTs or other nice classes. So let me just define this class now that I motivated a little bit why I'm interested in it. Following a little bit the notation introduced by Elba, we need a genus G, is the genus of our surfaces, and N is the number of mark points. And then we want the 2G minus 2 plus N is greater than 0. This excludes just a few cases. So the torus without mark points, and also the sphere with 0, 1, or 2 mark points. So these are the only bad examples. And then we need R, which is a positive integer, and S is an integer. And we need a vector of A1, AN, which are between 0 and R minus 1, such that this modular condition is satisfied. Now I want to consider the moduli space of curves C with mark points P1, Pn, such that there is a line bundle L that tensored R times is isomorphic to the log canonical to the power S, twisted at the points Pi by these coefficients AI, exactly as in Elba's talk. This moduli space has a universal curve, and there is a universal R root, and there is a projection on an MGM bar that forgets this spin structure. And so one can consider the Chern characters of this L, and these Chern characters have been computed by Chiodo, and this is the formula. So it looks a little bit complicated, but if you know the total Chern class of the Hodge bundle, you will recognize that the form is very similar. And in fact, if you specialize S is equal to 1, R is equal to 1, AI is equal to 1, R equal to 1, you will get exactly the Chern character for the Hodge bundle. And so the only difference here is that what used to be Bernoulli numbers, now they are enriched. They are not numbers anymore. They are polynomials. They are Bernoulli polynomials, and they're evaluated at these parameters. So what I wanted to say is that if you're not familiar with these classes, okay, the psi classes were presented by Elba, and the kappa classes are push forward of psi classes, and then this J are boundary divisors. So you can think as pinching the curve at a cycle. The point that I wanted to make is that even if this formula looks complicated, it in fact is very explicit. And then when you want to compute the cohomology, you just have to list all possible graphs and decorate them in all possible ways. So it's very implementable also. You can code it the computer. And so I want to define Chiodo classes as the push forward of the formal exponential of the sum over M of the Chern character Cm with these parameters. And then I just insert here x to the m as a degree parameter, something formal. And then this is the example we've seen before. If all the parameters are equal to 1, then the Chiodo class 1, 1, 1, 1, 1 is just lambda of minus 1. So in fact, you can produce a formula as a sum over stable graphs. By stable graphs, I mean just graphs in which every vertex is decorated by a genus, and then every component of this vertex is stable, meaning that every genus 0 has at least 3 special points, and every genus 1 has at least 1 special point. And then, so the sum over gamma is the sum over stable graphs, and the sum over W is the sum over decorations. So every time you have a leaf or a half edge, you decorate it with a number between 0 and r-1 in all possible ways, such that locally, the modular condition that we've seen before holds on every vertex. And also every time that you have an edge, if you sum the weights of the 2 half edges, you get 0 modulo r. And on the leaves, you decorate it with the AI that you have, that you start with. So again, this is a very complicated formula at first sight, but it's very implementable as well. So in terms of cohomological field theory, also related to Elba's talk, you take a vector space of dimension R, and then your Berliner form is again just a delta modulo R, and then the unit is just a formal sum of all your basis vector VA. And for those of you who like Givental formalism, this is the R matrix. So if you act with this Givental R matrix on the topological field theory given by this data, you get Chiodo class. So we know several things of this class. This is part of the point. We know it's Givental decomposition, so we can do many computations with it. And in particular, we can relate it to topological recursion because of Doss theorem. And the statement is that if you take the spectral curve given by x equal to minus z to the power r plus log of z, and y is z to the s, and as a Berman kernel omega 02, you take the canonical one, you run topological recursion, this parameter r and s, and you expect that this parameter r and s are related to Chiodo parameter r and s, and in fact, this is the case. So if you take the free energies after integration with omega gns, you get sum over the mu i's, then you get just some constants, some constant c, which doesn't matter too much. Then there is some prefactor that is a non-polynomial in the mu i's. So it's sort of mu I to the mu I divided by mu I factorial, but there are these brackets because this is, this comes from the division, as you can see here, the division modulo r. But the important part is that now the actual number that you produce is the integral over mgm bar of the Chiodo class, Rs, and your parameters AI are the reminders, are related to the reminders modulo R of the mu i's. So the point of this slide is that we now know what, well, since a little bit, we know what is the right spectral curve to give to the topological recursion theory in order to obtain the intersection theory of Chiodo class. So we can control Chiodo class with topological recursion. That's the moral of the slide. And so I don't want to enter too much in the details, but this is just a little bit of examples. If you plug R equal to S, in this case I call it Q, this ELSV formula was known to Johnson, Pandaripan, and Tseng, and the numbers that you have on the left-hand side are Hurwitz numbers. So they're counting covers of the sphere with prescribed ramification over 0 given by the partition mu. And over the partition, over the point infinity, you have a profile of the type Q, 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 Q. So this is the parameter Q that you need to insert into the Chiodo class. And in fact, you can give another proof of this formula using topological recursion. So this is a nice application, I think, how topological recursion can do something for algebraic geometry. Again, if you specialize s equal to 1, you recover the, so in this case would be q equal to 1, you recover the usual ELSV formula. And then there is a relation to Zwanking conjecture, which is now a theorem. And actually this will pop out later on in the talk, so we need it for the main part. If you consider Chiodo class with parameter r and 1, then on the left-hand side, you have the Hurwitz numbers with completed cycles. So again, you consider Hurwitz numbers, so covers of the sphere of genus G, and then the partition, the ramification profile over 0 is given by the partition mu. And then over the infinity, now you have nothing, and you have something that is unramified, so 1, 1, 1, 1, 1. And then all the other ramifications, you require them to be what is called R plus first completed cycle. And I will not enter into the definition of completed cycles because it's a little bit technical, but instead I want to show some examples. So completed cycles are called like that because they are what you expect. So the R plus first completed cycle is indeed equal to R plus 1 sheets of the cover that come together in one point. So that's the leading order. But in fact, you have a correction tail with genus defect. And for instance, if R is equal to 1, you have no correction at all. But already if you have R equal to 2, you see here, you have a correction with some weird coefficients. And in general, you will always have the leading term is equal to what you expect plus lower order terms. And in fact, these completed cycles, the main point of them is that they are related to the Okounkov-Panaripan, the Gromov-Witten-Hurwitz correspondence. So they are exactly the algebraic objects that you need to give to Hurwitz theory in order to equate Hurwitz numbers to correlators coming from Gromov-Witten theory of equivariant P1 target. And then you can put the two together. You can do completed cycles with orbifold profile. And again, you can control this with topological recursion. And the parameters here that you need is RQ, Q. This has been proved in a long series of papers by many people. And also you can do double Hurwitz numbers, meaning that you take now x equal to log z as before, but now here you have minus q of z, which is a certain polynomial in z, like that. So q of z is equal to the sum of these formal parameters qj times z to the j. And whenever you see such an expression, you can think that each of these qj's allow an orbifold profile with j sheets coming together over infinity. So you're allowed to use all orbifold profiles at once up to the top d. And then eventually you can send this d to infinity, or think of it that is sufficiently high, and therefore you can use any ramification and you have double Hurwitz numbers. And in this case, q appears both in the x and in the y. And then you might wonder whether there is ELSV formula for double Hurwitz numbers. And this is what we derived with the Borodon, Karev, and Elena Moskovsky. And in fact, the ELSV formula that we derived is derived from orbifold Hurwitz numbers for given d, and then you deform the spectral curve to obtain some formula that looks very complicated, but the main point is that you sum over k here, and then you have integrals over mg n plus k. So you don't just have one moduli space, gn, as you would expect from the correlators, but you have that one, and then you increase the number of mark points as much as you want, but in fact, this sum is finite. So you will have, starting from Gn, you will have a certain amount of moduli space which are involved. And the class that you integrate is again Chiodo class. Yes?
Danilo?
Yes?
Can this be viewed as a weighted double Hurwitz number with some weight factor, one weight generating function?
It's not straightforward, and I'm not sure that it's completely general. So I think ELSV formula for weighted Hurwitz numbers will contain more information than this formula.
So there's no equivalent weight factor which would give this spectral curve?
I think for weighted Hurwitz numbers will be richer than this formula.
Okay.
But we have no such formula as of yet, I believe. So again, this formula was obtained by the formation of the ELSV formula for d orbifold Hurwitz numbers. And the nice thing again is that you have applications to algebraic geometry, meaning that you know that this expression should be a polynomial in the Q's just because of the definition of how we obtain this by topological recursion. But you obtain that in fact, it's not straightforwardly polynomial. So if you impose that it's polynomial, you have some tautological relations between the numbers. So when I say tautological relation, I have to be careful. It's not a relation in the cohomology, but it's a relation between numbers which are already integrated over the modular space of curves. And then another consequence is that if you consider Hurwitz numbers in which the ramification over infinity is total, so every sheet of the cover comes together in one point, Golden, Jackson, and McHill conjecture the ELSV formula. And we obtain one ELSV formula, which doesn't mean it's the only one or the best, but at least is one ELSV formula. And this again involves Chiodo class with a very peculiar parameterization. In fact, here you have DD in the first two parameters, like you did in the orbifold case. But now you have this peculiar phenomenon that the AIs here are intrinsically related to the first two. And this is something that plays a role. Okay, I shall not enter in details, but it's sort of this behavior in which the AIs are intrinsically related to the R and S. It's something that you don't see often. And so you can exploit this formula to obtain some unexpected tautological relation between numbers again. So for instance, if you now impose orbifold profiles on the left and orbifold profiles on the right, from Hurwitz theory, of course, you know, and it's trivial that if you swap the profiles over 0 and infinity, nothing changes. So the count of discovers is equal to the count of discovers, right? Because the ramification profiles correspond to central elements of the symmetric group, and therefore they commute. But from the point of view of integration of a modular space of curves, you obtain equalities between integrals over modular space of curves that have different n, different number of mark points. This is the degree divided by p, and this is the degree divided by q. Here you have Chiodo class that is of the form QR, Q, and then all the AIs are minus P. And here you have instead the PR, P, and all the AIs are minus Q. But they turned out to be equal. So this is another example of how topological recursion in a way can give something to algebraic geometry. And so now I will speak about Neuberg class, which I believe was treated way more in details yesterday. But just as a motivation for completion of these examples, you probably have seen that this is the spectral curve for the Weil-Peterson volumes of Miyazakani. So we are integrating exponent of kappa 1. And the curve that we need to take is just the Witten-Kontsevich for x, and y is the sine. But now if you take the cosine instead of the sine, what you get is the integral again of exponent of kappa 1, but now you intersect with Neuberg class theta. And so now these are volumes of modular space of hyperbolic structures on super Riemann surfaces. And so this gives, I think, a very nice application of the theta class. And the point in this presentation of the theta class is this definition over here. In fact, the theta class can be defined up to some prefactor to be the homogeneous degree 2g minus 2 plus n of a Chiodo class for a specific parameterization. So you have to take this x, this degree parameter equal to -1, the r is equal to 2, and s is equal to -1. And in fact, I mean, you could think, why should I take this degree? But this has a deep geometric meaning in the sense that this is the top churn of an actual bundle. So it makes way more sense to take the top of something. And so this is another application of Chiodo classes. Well, you've seen many of these yesterday, I believe, so I'll not repeat. And then Mazovich volumes, Alessandro will speak a lot about them, but I just want to mention in relation to Chiodo classes that the Mazovich volumes and VGN, up to some normalization with pi and some prefactor that doesn't matter, they are equal to, again, the integral of Chiodo class. In fact, I'm cheating a little bit because this is not an actual Chiodo class, it's Chiodo class to the -1 for the parameter 1 and the degree, 1 for R and -1 for S. But in fact, there is a way to restate this equality, putting here an actual Chiodo class. but for different parameters. We'll see this in a minute. But as a result of this theorem by Chen, Müller, and Sauvaget, the conjecture about Mazurowicz volumes that we made with several people holds true. And then in particular, you can decompose the Mazurowicz volumes of the principal strata of quadratic differentials as a linear combination of Hodge integrals. And here, this is peculiar that the psi classes are integrated always to the power 2. And in fact, the relation is this one. So whenever you have Chiodo class, and here you have your degree parameter, and then you have 1 and then something called b to the -1. If you apply the involution such that a goes to -a and simultaneously b goes to 1 minus b, then you get rid of the -1. This is how you can pass from the Chiodo class to the Segre class, changing the parameters. And now you have a formula for Mazurowicz volumes in terms of integrals of actual Chiodo class without the -1. So you can wonder, but we have topological recursion for Chiodo class. So why can't we have a spectral curve for Mazurowicz volumes of the form of the shape of Hurwitz numbers? And in fact, we can. And so this is the formula. It's extremely similar to the one for Hurwitz numbers, with the main difference that this -1 here results in a -1 over there. And then you have to put a 2 because of the 1 minus b that becomes 2. Okay, last application, I believe, of Chiodo class. This is more of a curiosity. You can produce the Euler characteristic of the modular space of curves by integrating Chiodo class with parameter 1, 1, -1, and all the other parameters are equal to 1. And this follows from standard arguments. It's just a matter of recognizing somehow that the class that you have here is a Chiodo class. And as a consequence, you can split this class in the lambda -1, so the total Chern class of the Hodge bundle, times exponent of kappa classes. And now you can exploit this form to give a new proof of the very famous Hurwitz formula for chi. Okay, so with this, I wanted to convince you somehow that Chiodo classes is everywhere. And in particular is also in this last work with Alessandro Jacquet and Renier Kramer. And let me introduce a little bit first the motivation why we started this. Now we started this because we like topological recursion and we want to understand better how this works in other settings and for other integrable hierarchies. But also we came across motivation of another community that is more interested in Gromov-Witten theory of certain targets that in particular have complex dimension 2. So it's something more complicated than curves, even if you don't see something that is not a curve in this picture, but I will come to it in a minute. In particular, let me start from the connection that is here on the top. This is very well known, is Okunkov and Pandavipande. They relate the Gromov-Witten theory of curves to Hurwitz theory, and this is something we have seen before. So in particular, this relation is established via the completed cycles. So if you consider Hurwitz numbers with completed cycles, they correspond to Gromov-Witten of equivariant P1. And then there is another world that I will call the spin world here, and that is related to spin curves. So let me use now this definition over here. What is a spin curve? A spin curve is a curve with attached a theta characteristic, so a line bundle that squares to the canonical. Okay, and why this Gromov-Witten theory of spin curves is interesting? Because of point 1. Because it has been proved that the Gromov-Witten theory of Kähler surfaces with a small canonical divisor is entirely determined by the Gromov-Witten theory of spin curves. So if you happen to control this world, then these are the building blocks to understand the Gromov-Witten theory of much more complicated targets. This is why people want to understand.
Danilo, can I just intervene with a quick question?
Yeah.
Is there any direct way to connect up what you're calling spin curves with, let's say, what Paul calls a super Riemann surface?
There might be, I'm not sure at the moment.
I mean, when you speak about super Riemann surface, you're adding some kind of a Grassmannian variable, and that means generally there is a curve and there's some extra data, like this data characteristic.
Yeah, I'm not sure now. I'll have to think about it better.
Okay.
So this
Paul in the audience, by the way? Is Paul around? Paul Norbury? No?
Postpone this to later, please, because it feels like a very good question, but also a complicated one that would require some time and some analysis. So I would rather postpone it.
It might, well, John, they might have different combinatorics actually. R spins and supersymmetry, so it's not obvious. Okay, yeah, Danilo, so just continue, sorry.
Okay, so so this is why people are interested in this world. And now there is in fact a notion of spin Hurwitz numbers. And how would you justify that you inserted these particular Hurwitz numbers in this diagram? So the reason why people believe that these are the right Hurwitz numbers is that there is a conjectural Gromov-Witten-Hurwitz correspondence at this level, at the level of the arrow below. And this Gromov-Witten-Hurwitz correspondence in the spin setting is proved for the first cases, which includes, for instance, when the degree of the curve is low, I think 0, 1, 2, something like that. And also other examples. So that there are a few cases in which this is established, and people believe that is true in general. So there are explicit conjectures about this. And also the vertical relation on the right, well, the vertical relation on the left is just enriching the curve with a theta characteristic. Whereas you could wonder what is the relation between Hurwitz numbers that we know very well and Hurwitz numbers of this spin type. And this is what I would like to explain now. So let me start from Hurwitz numbers as covers. So if you start with by age, I mean Hurwitz covers which are connected now. So they depend on a genus G and on two partitions mu and nu. And what do you want to count here? You want to sum over branch covers over the Riemann sphere, which have profile mu over 0, mu over infinity, and then you want to impose some condition on the intermediate ramification. Depending on which conditions you impose, you get a different Hurwitz problem. Every time, so this F are actually equivalence class of branch covers, and the relation is that if you have another isomorphic cover that commutes with the branch points and leaves the branch points stay in the same place. And then you want to divide, if F has a lot of automorphism, you want to divide by the number of them, but often is just equal to 1. And so once you consider this number, there is Frobenius formula that we know very well that expresses these numbers as sum of characters of the symmetric group over irreducible representation of the symmetric group. And in particular, we want to focus on the numbers with R+1 completed cycles. So about the integrability of these numbers, they satisfy the 2D Toda lattice hierarchy. And if you specialize one of the partitions to the trivial partition, so you have no ramification anymore, then they satisfy the KP hierarchy. So now what is the relation between these numbers and the spin version? How do the spin version should look like? In fact, they look like the same with a tiny difference, which is fundamental. So you basically do the same. Again, you sum over the same F, except that here you weight with -1 or +1. And it's very important how to decide whether it will be a plus or it will be a minus for a given F. So each given F has an ARF index that I will define now. And this determines whether F it's called even if it's a plus or odd if it's a minus. In order to define this ARF, we also need to impose extra conditions on the ramifications. First of all, both the partition mu and the partition nu should be odd. So all their entries should be odd. And this is fundamental to define the ARF, because what do you do with the ARF? You're projecting on the sphere. And on the sphere, in fact, we just have one spin structure. So if you look for line bundle that squares to the canonical, you can just take O minus 1. So that's the only thing you have. You take a theta characteristic downstairs, and then you lift it upstairs. You lift it pull backing via F. This is not enough. You need to tensor this because you want to involve the ramification of F, and you take the ramification divisor of F. And because all the partitions mu and nu and also the intermediate ones are odd, the ramification divisor has even coefficients, and therefore you can divide by 2. So you twist O of the curve upstairs by the ramification divided by 2, and you tensor with the pullback of O minus 1. This is a sheaf on the curve. You can take its H0. So this will either be even or odd, and depending on that, you will have this formula. So I claim that this is the, well, this is not me that claims it, but I'm claiming it now in this talk, that these are the right candidates to fit into the diagram that was shown before. And so you might wonder, how many properties do we have about these numbers? There has been quite some work about these numbers recently by many people. So from the topological recursion point of view, but also not just from the integrability point of view. The substitute of Frobenius formula is Cunningham formula. And this expresses these numbers as characters, sum of characters, of the Sergeyev group over a reducible representation of the Sergeyev group. And the Sergeyev group is given by the Clifford group on which the symmetric group acts by permuting the generators. And again, we are interested in these spin Hurwitz numbers in which the intermediate ramifications are some analogous of the R+1 completed cycles. It's possible to define it, where R this time has to be even because we want R+1 to be odd. So we always have to be careful about these even odd conditions. And their integrability is now of the type BKP or small BKP. And the first thing that you notice about these numbers is that there are no possible simple ramifications allowed. And in principle, you could think this is a problem, right? What do we do in Hurwitz theory? The first problem, the easiest problem that we want to study is simple Hurwitz numbers. What are simple Hurwitz numbers? You take all the intermediate ramifications and you acquire that they are simple. So there are just two sheets that come together in each branch point. And that's it. That's the easiest to study. But here, because all the ramification profiles should be given by odd numbers, 2 is not odd, so you don't have it. The simplest possible problem in this setting is 3. So you start from completed cycles which are non-trivial. So the easiest thing is hard in the spin case.
Yeah, Danilo, could you just go back for a moment?
Yeah.
I've heard this Sergeyev group mentioned several times by the Russians, but I never understood exactly what this Sergeyev. This is a finite group, which is a semi-direct product of a symmetric group. Now, what is this Clifford group in mu? I know a Clifford group, but it's not. It's not this. So, what do you mean by this Clifford group?
Yeah, I don't want to give. I didn't want to give the definitions. It's in our paper, but anyhow, like you have these generators Xi1, Xi(n), and they have the usual Clifford commutation relations. And you also have epsilon.
But okay, let's say that the order of mu is 2. What is the Clifford group of 2? What is its order?
It's all in our paper. You can look at the precise definition, but it's a finite group and has just a little bit more elements than a symmetric group.
So specifically, the order, if I can just interrupt, of Clifford's D, say, is 2 to the power D plus 1.
2 to the power what?
So you have these D, you have D involutions Xi I,
yeah,
and an extra involution epsilon,
oh,
and some commutation relations.
So does it look something like a? Does this Sergeyev group look like a Weyl group or something?
I would think so, yes. Not quite sure.
Mm-hmm. And the conjugacy classes are also labeled by partitions or something else?
Yes, they are labeled by partitions, but one needs to be careful because there is this subtle bijection between odd partitions and strict partitions. And one corresponds to the conjugacy classes and the other one to the irreducible representations. So you have the whole picture. I mean, in the symmetric group, it's a coincidence, the fact that the two sets coincide. Here they are in bijection, but they are not identical.
Right. But last question, I don't want to interrupt you more, but it is true, is it that the transition matrix, which takes you between the Schur functions and the Q, between the Q Schur functions and the power sum symmetric functions, have these these Sergeyev group characters, yes, exactly, as their entries.
That's how you can define Q Schur functions as well, yes. Yes, I mean, it's in our paper. If you want all the definitions, they are in our paper. And the picture, as you expect, goes through identical with a few modifications. Yeah. I would say all the principles are preserved and the objects have a little bit of a different shape, but all the statements that you would expect from the symmetric group, they still hold in some slightly modified form.
Yeah.
Okay. So let me define instead these numbers from the semi-infinite wedge formalism instead of defining the completed cycles. So this is the usual picture for Hurwitz numbers. We start from chart fermions. So we have this psi and psi star with the usual anti-commutation relations. And then starting from the vacuum, we can apply the psi to define these elements V lambda. And then we take this element EJK, which are defined as the normal ordering of psi j, psi k star, where this a semicolon before and after for normal ordering stands for just the product minus the vacuum expectation of the product. What is the vacuum expectation? If you have some operator in the psi and in the psi star, its vacuum expectation is defined to be the orthonormal byproduct between the operator applied to the vacuum and the vacuum. And this is defined by imposing that all the V lambdas are orthonormal. So the product between V lambda and V lambda is 1 for each lambda, and is between V lambda and V mu, for mu different from lambda, is 0. So you apply patiently all the psi and all the psi stars, and then you count how many times out of the application of O you actually get the vacuum. So once you have this building blocks EJK, now you can define this Okunkorf-Monary-Pande operators FR to be just the sum over all k half integers. And you take k to the r, where r is the index of this operator, and you take EKK. And as well, you can define the operators alphas in a similar way, except that the operators FR has energy 0, whereas the operator alpha has energy, alpha m have energy m. And these are the usual commutations between the alpha operators. So what is important for us is that now expressing Hurwitz numbers in this setting is very easy, because what is the Hurwitz numbers hg mu? This is just the vacuum expectation of the following thing. So on, say, 0, you have an unramified profile. So an unramified profile is of the form 1, 1, 1, 1, 1. So you just use alpha 1. So basically the correspondence is extremely clear. The index of the alpha is the ramification profile. So because you want 1, 1, 1, 1, 1, you take that, and then you take the exponent so that you divide by the automorphisms. And then on the other partition, you have the mu, and therefore you just take alpha of minus mu. This time you have to take the minus because you're hitting the vacuum, otherwise it vanishes. And also you divide by this mu I because you want to normalize the commutation relation. And in the middle, you want completed cycles. So you actually take these operators F and then you plug them in here again. You can use them as many as you want, provided you multiply by a formal variable u. And at the end of the day, you just take u to some power. So you can do the same thing for the spin version. This time you start from the psi's, you have psi and psi star, and now you define some fermions which are called uncharged. And you define them as a linear combination. In fact, you just need just two of them. You just need one psi and one psi star with this normalization. And this is the anti-commutation between the psi's. Now you want to define the V lambda as before. Now you want to do this only for strict partitions, as we mentioned before. And depending on whether this partition is of even length or odd length, you have to insert one more psi 0, but this is not very important, and also square root of 2, but this is just normalization. Basically, the picture goes through in the same way. Now you define as before, you had the A, the E, JK, now you have the F, JK, and you define them very similarly. In this case, you don't need the normal ordering, it's already okay as it is, and you define the vacuum expectation just as before, and you have very similar definition of the operators F and the operators alpha. Because these uncharged fermions, they behave a little bit differently. You, in fact, don't need to sum over all integers, but you can normalize them, summing over half of them. But the commutation relation looks basically the same, except for this division by 2. And now the statement is that the spin Hurwitz numbers, they, again, can be computed via vacuum expectations of these uncharged fermions. And you do the same as before. You do exactly what you expect. You take the vacuum expectation again of lambda 1, because you have anonymified. And on the other side, you take lambda minus mu. And in the middle, you use the completed cycles operators F, and you take the right powers of u up to some normalization of 2. So my point here is that you can build a completely analogous world of fermions. In this case, will be uncharged fermions, but there is a definition of all the operators F and alpha that you need to express your Hurwitz numbers as vacuum expectation of these operators. And this automatically implies that the partition function of these Hurwitz numbers is a BK-Peter function.
So,
Excuse me, may I ask you?
Yeah.
Yes?
I don't know, somebody else was speaking.
Maxim Kazarin. I would like to ask, is there a bosonic side of this picture?
Thank you, Maxim. This is the next slide.
Okay, my question is also related, so maybe I'll slip that in. So, okay, you've given here a fermionic representation of this thing, but can you tell me combinatorially what it means? Is it enumerating factorizations in the Sergeyev group?
Yes, but you have to wait with the right minus and plus ones.
So can you say explicitly what it is in terms of enumeration of factorization?
I'm sorry to interrupt, but we must be in time for Bertrand's talk.
Ah.
Yes, but John, you're very expert in these things, and I believe this would be, I don't think it's hard. I think it's almost straightforward from your work applied to the usual Hurwitz numbers. You just need to insert the right signs in the right way, but it should always also be a work on the KD graph of the Sergeyev group. I think it's almost straightforward. One just has to write it down carefully. Okay, so let me reach the main part. Otherwise I will be late. So this is the question of Maxime, more or less, if I understand correctly. So for the usual Hurwitz numbers, we have the Okounkov-Panaripand operators, so the bosonic world. We have this magic Matkal E. Why they are so good? You define them this way. So as you see, if you remember a little bit how the operators were defined, you can guess that they are sort of an interpolation between the operators F and the operators alpha. They have charge because it's K plus M, so their charge is M, but also they don't have 1 as a coefficient, they have exponent of something as the F operators. And in fact, it turns out that they are very useful because if you specialize Z to 0, you get the alpha. And if you specialize M to 0, you get the F up to some normalization. And the vacuum expectation is given by 1 divided by the hyperbolic sign. Now, the reason why these operators are so useful is that they are closed under commutation. If you have a commutation of E, M, Z, and E, M, W, this is equal to a curly E operator again of energy M plus M, as you would expect, but the argument is just the sum of the two variables, and you just need to multiply by a hyperbolic sign. And this equation is so powerful, you can do so many computations with it. So this was also a very important step of the Gromov-Witten-Hurwitz correspondence. So we were using this equation in several works before, and we thought like it would have been very useful to have the same relation for spin. And in fact, if you define the spin version like that, it turns out that again, you have the same properties. You have that if you specialize the variable to 0, you have alpha. If you specialize the energy to 0, you have F. And the vacuum expectation now, what you need instead of a hyperbolic sign is the hyperbolic cotangent. And then the commutation relation looks like is in two pieces. The first piece is what you expect. Again, here it's curious because before you had hyperbolic sign and hyperbolic sign, but now you don't have it anymore. Now you have hyperbolic cotangent in the vacuum expectation of a single operator, but you have hyperbolic sign in the commutation relations. But also you have one additional piece. You have what you expect. So this is basically the old world, the non-spin world, plus -1 to the n divided by 2. Again, you have hyperbolic sign, but here you have a plus instead of a minus. And here you have a minus instead of a plus. Of course, the energy is forced. You don't have a choice here. You have to put plus. I mean, it would be absurd if the energy wouldn't be conserved. Plus, you have here some extra property. They satisfy some parity. And so now we thought, like, let's see if we can repeat the same applications of this algebra in the spin world. And okay, so this is something that you can find in our paper. It's a careful translation of the two worlds. So maybe this is also interesting to John or whoever wants to understand a little bit better, the explicit correspondence. And one thing we could do with this commutation formula is that what is called strong piecewise polynomiality and wall crossing formula. So how does it work? If you consider the set of partition mu and nu, such that they are integers, but now you have to remember to add odd here, because otherwise the spin Hurwitz numbers don't make sense anymore, such that they are of the same size. And now you consider all these possible equations over here, some of the mu I is equal to some of the nu j's for all possible subsets, and you call this the walls. What happens is that inside each chamber, which is defined by the complement of the walls, there is a polynomial that gives you the Hurwitz numbers. So the function that associates to mu and nu the Hurwitz number of the spin type is piecewise polynomial. And in each chamber, you have an explicit degree decomposition, and you see that many degrees die and only those ones survive. Moreover, if you have two chambers which are adjacent, so close to each other, and they are only separated by a single wall, you could wonder how this piecewise linear function behaves in the transition. So this is the wall crossing phenomenon. And then in fact, it behaves as in the non-spin world, as a quadratic explicit expression in the generating series of the spin Hurwitz numbers. So I didn't write the formula because it's a mess, but it's morally the same phenomena as in the non-spin world. And now let me talk about the topological recursion. This is the spectral curve for the Hurwitz numbers with completed cycles. And our main conjecture is that this is the spectral curve for the spin world. So we found this formula by semi-infinite wedge by computing the unstable energies 0,1 and 0,2. So you just need to add this piece over here to recover the spin Hurwitz numbers. We tested this numerically, and what is interesting about the spectral curve is that it does not satisfy the axioms of the spectral curve, in the sense that now you have that the two local coordinates have poles when approach different ramification points, and this is not allowed. And what happens is that you have two S simple branch points, but they are paired. And what I mean by paired is that there is an underlying group, that is just Z over 2Z in this case, and these 2 points are in the same orbit. And this led us actually to consider G equivariant spectral curves and consider the quotient. What is interesting and very recent is that Alexandrov and Chiodo proved this conjecture and applying to the BKP hypergeometric tau functions methods of an earlier paper with many people that are here. So Bichkov, Duni, Merkovsky, Kazarian, and Chiodo for the KP hierarchy. They apply the same strategy for the BKP hierarchy. And I don't have the time, but I think I explained this during the topological recursion seminar, so maybe it's recorded in the talk. There is a notion of equivariant G spectral curves, and you can quotient spectral curves to arrive to reduced spectral curves. And what is interesting is that the correlators of the reduced spectral curves are equal to the correlators of the non-reduced, and the only difference is a prefactor. And this prefactor is the cardinality of the group that acts to the power 2G minus 2 plus n. And our spectral curve is just a Z over 2 equivariant spectral curve. About IHES V formula, and I concluded, just need 2 minutes, if I may. Swanking conjecture for Hurwitz numbers with completed cycles look like that. And here we had Chiodo class, whereas we exploited the DOS theorem in this case, which required a few small adaptations to the spin Hurwitz numbers. And we find some class here. And then we wanted to see how this class, how much this class differs from Chiodo class. This is the question. And then using DOS theorem, we can get, as before, an expression over stable graphs. And if you remember a little bit the expression, I can tell you that it's exactly the same, and the only differences are signed in red. So the weights are odd now, instead of all the weights. And here, instead of having 2S, you just have S. And it may seem something small, but when you want to understand that this geometrically it's not immediate. And what turns out is that, in fact, the class that you had, that you might think is related to Chiodo class, is in fact something beautiful. Is in fact the Chiodo class times the Witten class that was also presented in Elba's talk. Except that you need Wittens for r equal to 2 in the modular space of true spin curves. And then you intersect that with the push forward of the Chiodo class that is pushed forward from the R spin world. So this is sort of an elevator that stops. It starts from the Rth floor, it goes all the way down to the second floor. There it meets the Wittens class, they intersect, and then they go down to the first floor. So this is the geometric interpretation of the class. And if you plug S equal to 1, so now R is equal to 2, you recover IHES V formula. So this is the easiest IHES V formula for spin Hurwitz numbers. And what is nice about them is that this complicated formula over here just becomes the double Hodge. And this is peculiar because we have IHES V formula for 1 Hodge and for 3 Hodge. And this is for 2 Hodge. I'm done, sorry, slightly over time. I want to thank your attention. This was... Sorry?
Thank you, Danilo. Yes, a very nice talk. As usual. So let's thank you first. Yes. We don't have much time for questions, but maybe one more.
I probably said too much already, but I have a comment.
Okay, John, yes, please.
Very quick comment, Danilo. There's a bunch of results, recent results. You didn't mention you didn't get around to mentioning the role of the BKP tau function as generating function for these spin Hurwitz numbers, but you do know that, of course. There's a bunch of results which relate, I mean, you know, they're Pfaffians and determinants and so on, which relate KP or two total functions as bilinear sums over BKP type tau functions. Okay, that's some recent stuff with Orla. This must have an implication for the Hurwitz numbers versus the spin Hurwitz numbers. There must be some bilinear identities which express the ordinary Hurwitz numbers bilinearly as sums over spin Hurwitz numbers. And I'm just suggesting that this is maybe a worthwhile avenue to explore, to apply these formulae, which are all published.
Sure, I think this will be very interesting. Yeah.
I think it has already partially been answered actually by Sasha Alexandrov and Sergei Shatlin in their paper that Danny mentioned. That they do give a bit of a relation in this regard as well.
They give a quadratic relation between ordinary and spin?
Yes, in a sense. Although in higher spin, it kind of gets complicated. I think there's no straightforward relation, but they give it quite an explicit thing. Sasha, maybe you can answer.
Yeah, it's just, there is a standard relation coming back to Jim Miller between KP and BKP tau function. So it's a particular case for hypergeometric tau function.
Yeah, but what I'm saying is not that old standard relation which just says that one is the square of the other. There's a much more refined relation which applies to not just individual KP tau functions, but to whole lattices of KP tau functions versus BKP tau functions. I suggest to look up the papers. They appeared in the last year or so, and it really is much more general than the old one, which relates, I mean, which is obvious from the relation between Pfaffians and determinants. It really is a sum over BKP tau functions rather than simply a square.
Okay. I think that we now have to thank Danilo again. Oh, I have questions, but well, we don't have much time. But really, it's just to draw your attention that nowadays we have this new development of this topological recursion with changing two-point functions, right?
Mm-hmm.
Because there was the same phenomenon, I think, in paper by Normdo and others, also related to spin Hurwitz numbers.
Although I think this particular change of the Berman kernel, in principle, it does not satisfy the regular axioms of topological recursion, but I also think that Bertrand has a way more general view, also partially written down with Raphael Belliard, about cameral covers that would give a more general explanation of this phenomenon.
Yes, and we expect the same phenomenon for other models, at least for some models that I was studying like 2 years ago, never published. But okay.
Very interesting.
So Danilo, let's, everyone thanks Danilo again. And I think that we are about to move now to topological recursion seminar, to Bertrand's talk. So I send the link for those who don't have it, right? Let me just say